Hey guys, Greg here. Today we're going to talk about various sorting algorithms, and feel free to look at the video description or the timeline and skip to whichever sorting algorithm you want to see. Okay, so the first sorting algorithm we're going to cover is called bubble sort. There's basically a bubbling effect where elements will fall into their positions. Okay, so we start this by placing an index I at position 1, and then we compare what's at position I to position at I minus 1. And we ask if we want to swap their positions. Well, we're trying to make the numbers go in ascending order, so we're trying to make them increasing. So if the number on the left is bigger than the number on the right, that means that they're misplaced, and so we'd want to swap. However, we can see the number on the left is actually smaller than what's on the right, so we actually are happy with these positions, and we would just increment I. We can see what's on the left is greater than what's on the right, and so we would rather have these positions switched, so we simply just swap these. Okay, so we did our swap. We are going to increment I. We are going to switch these over as well. And let's just go through and swap everything we can here. So these two are going to swap. We move this over. These two are going to swap again. Notice this 3 is kind of bubbling up over to the right. We would increment I. This 7 is not going to swap with the 3. We move this over, and this is going to swap with the 7. And when we move the I over here, the 2 at the end is also going to swap with the 7. So notice here that the last position actually fell into place. Now, as you can see, I is at the end of the array, but the job is not done. They're not totally sorted. So basically, we would need to do this again until they are in sorted order. So we start I here, and we see we don't want to switch positions. We would move over here. We do want to switch these two. We move over here. We want to switch both of these two, and these two are actually going to swap as well. When we move over here, these two will not swap, but when we move over here, the 3 is actually going to get bubbled to the very end. So that's why it's called a bubble sort. You can see the biggest element is kind of bubbling over to the position on the right. Okay, so when we get to the end, we move back to the beginning because the job is not done. It is not sorted yet. And so we see here, we should not swap those. But when we get here, we're going to swap the -3 with the 1. We are going to swap this -3 with the 1 as well. And notice at this point, we actually are sorted. And so we'll get to the end of the array, get back to the beginning, and we actually are totally sorted here. So as you can see, we're basically moving I through the array several times here. That's going to create kind of a nested loop structure. And so this is going to have a time complexity of big O of n squared, which is quite slow. But luckily, it does have a space complexity of O of 1. So we're doing this, you'd say it in place. This is an in place sort, meaning we're just shifting the array elements that are in place here. We're not creating a new array. Okay, so let's code up this bubble sort. Okay, so to do a bubble sort, well, as we said, that has a time complexity of big O of n squared, and it has a space of O of 1, so that means it's doing it, quote, in place. Okay, so let's say we had this array of values. It's going to be the same one that we saw. So we'll define a function called bubble sort, and that's going to take an array. So we'll get n is equal to the length of that array, and then we'll set this flag, which is equal to true, and that basically just means we're not done yet, and let's assume that we're not done yet. So then while we have a flag, well, then we'll go into this loop, and we'll set here that the flag is false. Now that we're in this loop here, we're actually going to change it to false to say that, okay, we'll assume for now that we actually are done, and if we do any swaps, then we'll change it back to true so that it can run the loop again. Okay, so then we'll do for I in the range of 1 to n, so these are the inclusive positions of 1 through n minus 1. Then all we ask here is if the array at I minus 1, if that is bigger than the value at array at I, that means we'd want to swap. And so if we do need to swap here, then we'll set our flag back to be true. Since we did a swap, we'll want to run this thing again. We'll only stop running this when we don't do any swaps. So that just swaps these two positions. And that's actually all there is for bubble sort. It's really easy. If you call bubble sort on A, it's going to sort A in place. So if you output A, you will see that it is now in sorted order. And again, you can see that n squared time complexity because we do have a nested loop like this. And if you wanted to do this in the opposite order, so in descending order, then you would just flip that comparison and now it's completely reversed. But generally, we do sorting in ascending order. Okay, now let's cover an algorithm known as insertion sort. So we would again place an index I at the position of 1. So basically the idea of insertion sort is that you have a sorted area of the array. For now, it's just the first position, and an array of 1 is always sorted. And then you also have the rest of the array, which is the unsorted region. And basically over time, you're going to place or insert elements from the unsorted region into the correct spot of the sorted region. And so what you would do is create an index j that is actually going to start at I, and we're going to ask if we should swap positions j and j minus 1. We would not want to swap positions because the element on the left is actually smaller than the element on the right. And so basically what that means is that this area is now the sorted area. As you can see, -5 and 3, that is a sorted array. So we inserted the number 3 into the sorted region. Now we are going to insert the number 2 into the sorted region. So again, we'd get an index j, set that equal to I, and we would see if we want to switch these two. Well, yes, we actually do. Okay, we switch those, and then we decrement j. Do we want to switch these two? No, we do not. So that tells us that now this is the sorted region. As you can see, this is a sorted array as well. Okay, so we move over I, and now we're going to insert 1 into the sorted region. So we set j equal to I, we switch these two positions, we decrement j, we are going to switch these two positions as well, and we decrement j, and we again have a sorted region of the array that looks like this. We increment I, we are going to insert this number into the sorted region, we are going to swap these two positions, we move over j, we swap these two positions, we move over j, swap these two positions again, and we are not going to swap these two, meaning this is the sorted region. Okay, I'm actually not going to finish this off because I think you get the hang of it. Make sure you do this on your own. Okay, so once we finish this off, this is the result that we should get. And again, basically what we're doing here is we're taking an index I, and we are going to set j equal to I and potentially decrement j all the way to the beginning. So say that I was over here, for example. Well, then we'd have j here, and j would one at a time go backwards through the array. So essentially what you're doing here is still a nested for loop. You're incrementing I, and when you do that, you set j, and j goes backwards through most of the array. And so again, from this algorithm, you are going to get a time complexity of big O of n squared, and it's also still going to have a space complexity of big O of 1, or constant. Okay, now let's code up an insertion sort, and this is again going to have a time complexity of big O of n squared, and it'll also do it in place, so a space complexity of O of 1. Okay, so let's get that same array. We'll just call it b this time, and we'll define a function called insertion sort, which takes an array. So again, we'll get n is equal to the length of that array, and we'll do for I in the range of 1 to n, so it starts at position 1 and goes up until n minus 1, the end of the array. And we have this nested for loop with j that kind of goes backwards starting at I. So for j in the range, we'll start it at I. We actually write here 0 and -1. So what this range is we start at I, and this is actually the end exclusive. And since we're going down, we're actually decrementing j, so this 0 index is actually exclusive. It means the range of I until 1, actually. We don't want to use the 0 index because then we would reach out of bounds when we ask for j minus 1. So then what we would do is if the array at j minus 1, if that is greater than the array at j, so if that is true, you would want to swap these positions. Okay, and otherwise here, if that wasn't the case, what we're trying to do here is basically take I, insert what's at the array at I into your sorted region on the left. And so if that comparison is actually not true, well, that means that you don't need to do any more swapping, meaning that it's in the correct spot. And so you basically just break out of this loop here. Okay, so that's actually all there is to it. You would just run insertion sort on B. That is going to sort B in place. If you output B, you will again see that same sorted order. Okay, now let's do a selection sort. So the idea behind selection sort is we place an index I at the first position, and you want this position in the array to be replaced with what is the minimum value in the array. Because it's the first position, you would want the smallest value to be there. And so basically you would get an index j equal to I, and then you would push j through the array searching for the minimum index. And so as it does that, you would basically discover this index, we'll call it m, is the minimum index. It is at position 4 with the value of -5. And so then basically you would just swap these two positions because we want this position to be -5, and we also don't want to lose the fact that there's a -3 in here. So we would end up just swapping these positions, what's at index m with index I, and now we can see that this position is sorted, and we can just do this again. So if we increment I, and then we set j equal to I again, we'll we'll push j through the array looking for the smallest value in this region. And so similar to insertion sort, this is basically our sorted portion of the array, and this is our unsorted part of the array. Okay, so we would push j through the array, and we would see that the min index is either 4 or 5. It doesn't matter which one. So we'll say that it was 4, and then we would just swap these positions here. So what's at I with what's at m, we swap these positions, and we would increment I, we would set j equal to I, and we would keep doing this. And notice that this is now our sorted portion of the array. Okay, so we set j searching for the minimum index. We would see that it is at position 5 with a value of -3. We would end up swapping these positions here, and that's all I'm going to show you for this algorithm. So please, as an exercise, try to check the rest of this out yourself. Okay, very similar to bubble sort and insertion sort, the time complexity is going to be big O of n squared, because essentially we have an index I that is traversing through the array, and we get another index j which is going to traverse it as well. That is done in a nested pattern, and so you get an n times n, or an n squared, and the space complexity of this again is in place. It has a constant space solution. Okay, now let's code a selection sort. And again, the time complexity of this is going to be big O of n squared, and the space complexity is still in place, so it's still constant space. Okay, let's get that same array, but call it C here. So we'll define a function called selection sort, which again takes an array. We'll again get n is equal to the length of that array, and we send I through all the valid positions of the array, so 0 to n minus 1. You can do that with for I in the range of n. So that's implicitly just 0 to n minus 1. And right now we'll assume the min index is just I, and we'll try to look for the actual minimum. So for j in the range of I until n, so this is starting at I, going up until n minus 1, and you can actually start this at I plus 1, because you actually already set min index equal to I, so we can start at the next one. And we're just looking for the minimum. So if the array at the position of j is less than the array at our current minimum index, well, that means we found a better min index, and so you would just set min index equal to j. After we go through that loop there, that is going to find the minimum index, and then you would just want to swap what's at position I, so array at I, with what's at position of the minimum index. So this just swaps their positions. Okay, and that is the idea behind selection sort. So we can just run a selection sort on C. If you are to output C, we will again get that same sorted array. Okay, now let's do a merge sort. So merge sort is a recursive algorithm. It's very, very fast, and you might see it be called a divide and conquer algorithm, and we'll see why shortly. Okay, so what we're going to do is get an index m to be the middle of this array, and you can get this formula pretty easy if you have n is equal to the length of the array, and in this case, if you count this, we'll actually see we have 9 values. So if n is equal to 9 here, well then the middle index is just going to be the length over 2 integer division. So that would be 9 over 2, which gives 4.5. That rounds down with integer division just to 4. Okay, so that would show you that your middle index would be at position 0, 1, 2, 3, 4. Okay, but for now we have m as our middle index here, and that basically divides the array into 2 different pieces. And so we would split this out into 2 different sides here, -5, 3, 2, and 1, and then the right will be all of the stuff including m. Then we would keep doing the same thing on these other arrays. So this is going to split into 2 pieces here, -5, 3, and the right side is going to be 2 and 1. And over here, your left side is going to be -3 and -3, and your right side is going to be the array of 7 and 2 and 2. Okay, we have some more splitting to do. So this is going to split into just the array of -5 and just the array of 3. This is going to split into just the array of 2 and just the array of 1. This will split into both sides are going to be -3s. And on this side, you will have a 7, and on the right side, you will have a 2 and a 2. And there's one more split for this one to do. This would split into each of these are going to be 2s. You can see that now we've split everything into just an individual element. So each of these pieces here are what we call the base cases, and that's very important for our recursion here, is since we have these base cases, we stop when the array is just a value of one element. Now what's very interesting about these base cases is that if you look at any one of them, trivially, they are a sorted array. If you have an array of just one element, it doesn't matter what the element is, it is in sorted order. And so here, we are at this level here, we'll pick out these two, where both the left side and the right side, they're both sorted arrays. And all of this stuff we've done is the divide step. So we are dividing the array into 2 pieces recursively. Now we're going to do the conquer step, which is is basically saying that, okay, now that each of these things are sorted arrays, well, now we are going to merge these arrays together. So you're trying to create a new array, which is going to be of size 2, and it's going to be these two in sorted order. And it's pretty simple here. Basically, you would just say, well, you'd prefer the -5. Okay, the other choice is the 3, so we would have that. Okay, cool. We have replaced this with the sorted array, and it turns out it's exactly the same as it is up here. -5 and 3 is a sorted array. Okay, now let's do it for the 2 and the 1 here. And so that's pretty easy. Basically, all you would do is just take the 1 first, so we'll just swap them here. It would be 1 and 2. The -3s is very easy. It doesn't matter at all, so those two are sorted. Now at this step over here in the bottom right, we'd have 2 combines with 2. Well, that's going to be 2, 2. Combine 7 and 2 and 2. The first thing that you would want is this 2. The second thing you would want is this 2. And the third thing you would want is this 7. So we would want the sorted array of 2, 2, and 7. And now everything at this level, all of these things are sorted arrays. So it's called merge sort because we need to merge these two sorted arrays together. Both of these two are sorted on their own. We merge them to make a sorted array. And you can merge two sorted arrays in linear time. That's because if you call this array L and this one R, well then basically you would have an index L for the left array and an index R for the right array, and you're basically trying to create an array of length 4. So we're trying to fill up these various spots right here. So what you would do is say, do we prefer the left array at L or do you prefer the right array at R? Well, -5 is smaller, so we would prefer using L. So we would make this first value be the -5, and then we would increment L over. Now do we prefer the 1 or the 3? We prefer the 1, and so we're going to use the 1. We move R over. Do we prefer 2 or 3? We would prefer the 2. We move R over, and then since this one went out of bounds, we basically just want this to be replaced with the rest of this array, which is just one element. So this is going to be replaced by the 3, and we'd move L over. They're both out of bounds of their arrays, and so now we can replace this whole stuff with the sorted array, and so now we have the sorted array of -5, 1, 2, and 3. So let's do this pretty quickly here. We have L and we have R. The first thing we're going to want is the -5. We move L over. The next thing we would want is the -3. We move R over. Then we would get -3. We move R over. We would prefer the L, and so that is going to be 1. We move L over. Either of them are fine because they're both 2s. We'll just use L, so we'll get a 2 here and move over L. We'd use R with a value of 2. Again, we would use the 2. We move R over. We'd use L with the value of 3. We would get L to the end of the array, and we just have all the stuff left here, which is just one element, and so this last thing would be a 7. And so this array would be replaced by its sorted version, which is this array right here. Okay, so let's think about this. You can see this basically has a recursive tree, and that tree is going to have a height to this. And that turns out that that tree is going to be roughly log base 2 of n, because basically you are splitting the array into 2 halves every single time. And so if you keep doing that, if you take an array and you keep splitting it into half over and over again, well, that is basically dividing the array by 2 every single time, which gets you that log base 2 of n. So if the height of this thing is log base 2 of n, and to basically complete one entire level here, well, this is all of the elements together, and so to complete this whole level, you would have to just traverse through each of these things, and so it's going to be O of n to do that. And again, if you were looking at this level here, well, again, that's going to be an O of n operation to merge them together. You'd get a total time complexity here of big O of n times log base 2 of n as your runtime, which is very, very fast. Now, because the recursive call stack takes up space and the height is log n, the minimum required space is actually log base 2 of n. But as we'll see, we actually are going to have an O of n space just because we write it in a way which actually stores space per level. But you could actually avoid that, although as we'll see shortly, merge sort is hard enough to code as is. Okay, now let's do a merge sort, and this is a pretty tricky one. It's a cool recursive algorithm, so make sure you do understand it. It has a time complexity of big O of n log n, and the space complexity, our version is going to be O of n, and we'll see why. It actually can be done in log n, but this is a lot harder to write, and it's already pretty hard to write as is. Okay, so we'll get that same array here. We'll just call it D, and we will define our function called merge sort, which takes an array. Now this function is recursive. What it does is first gets the length of the array as usual, and then our base case for the recursion is if n is equal to 1, so if we have an array of size 1, well then you just want to return your current array. So we'll see why we want to return the array shortly. If you have an array of just one value, then it's sorted. And although you don't really need this, if n is 0 or n is equal to 1, you would return the array. So if you have an empty list, that's sorted too, although you actually don't need that case because, let's just talk about that briefly. If you did have an array of say 2 elements, well then you would get the left side is one of them and the right side is the other, and so they'd both be split into just the array of 1 and the array of 2. And if you did have an array of just one element, so either this or that, well then that also will get caught by that base case. So in merge sort, you actually won't end up with an array of size 0. Okay, otherwise, if we didn't get hit by the base case, we have an array that's bigger than size 1. We'll get our middle index m is equal to the length of the array, integer division by 2, so the midpoint. Our left side of the array is going to be the array up until m, get all of the stuff from the beginning, up until but not including what's at m, and then the right side will be array at the opposite, m colon, which means including m will get all of the stuff starting there from the end. And this is exactly why it's O of n space. This line here, it actually does generate a copy, or basically a copy of a slice of the array, and so that is using extra space. Technically, you don't need to do this, and you could do it by using various indices, although it's pretty tricky to do that. Then the very clever part of this is that if you have 2 arrays here, well, you want to make sure they're sorted before you do any merging. And so this is the recursion. You would set L equal to the merge sort of L, which basically sorts L, and then you would get R is equal to the merge sort of R. Now that could be a lot of recursion there, but after you're back from this step here, you basically have 2 arrays that are both sorted L and R. So if both L and R are sorted at this stage, well then you can actually merge them in linear time. And you would do that by creating a new sorted array, which is equal to, for now we'll just set it equal to a list of n zeros, and this line is again taking up O of n space. So if you have these sorted arrays L and R, then you want to merge them with some indices, so we'll set L and R lowercase are both equal to 0, and we need both of the lengths as well, so we'll get L len is equal to the length of L, and R len is equal to the length of R, and we're going to merge them by sliding these indices L and R across their respective arrays. Now we just need one more index here, I is equal to 0, so what you would do is first, while L is less than L's length and R is less than R's length, so while both of the indices are in bounds here, you want to compare their positions and take the smaller one. If the array of L at its index is less than the array of R at its index, then that means you would want to choose L. So we would set sorted array at I equal to L at its index. And then you use that value from L, so you'd want to increment that. Otherwise, you are in the other case where you'd want to use R at its index because it's smaller, and so you would set sorted array at I equal to R at its index. And then you would increment R by 1. And either case here, whichever one you chose, you would definitely want to increment I because you put one value into that sorted array. Okay, so this is what helps merge them together, but we're not done yet because one of these 2 indices would have went out of bounds. This only runs while both of the indices are in bounds. If say for example L went out of bounds, well then there would still be stuff in R, and we just want to use all of that. You would do while L is less than L's length, you would want to exhaust the rest of L, and so you would sort an array at I is equal to L at its index, and then you would want to increment both of them, so L plus equals 1, I plus equals 1 as well. And otherwise, if there was anything left in R, so while R is less than its length, then you would want to set sorted array at I equal to R at its index, and you'd want to increment both of those, R plus equals 1 and I plus equals 1 as well. Okay, so this is basically the merge part. You merge the 2 sorted arrays together. Okay, let's zoom out a little bit more here. So then all you would actually do is return your sorted array. Now this function is so big, it doesn't even really fit on the screen. If we run merge sort on D, let me just confirm to you that that works. So it's a very clever algorithm, and if you don't fully understand it, then that's kind of understandable, but do try your best to get a rough understanding of the idea. Okay, now let's do a quick sort, and similar to merge sort, it's also a recursive algorithm. In my opinion, it's a lot easier to do than merge sort. So basically what you do is you pick a pivot, which will just make the very last element of the array, and then we divide the array into 3 different pieces here. The middle is just going to be the list of the pivot itself. The left will be all of the elements that are less than the pivot, and the right side will be all of the elements that are greater than the pivot. So all of these elements here, what is less than, and will actually allow equality as well. So what is less than or equal to the pivot of 2? Well, we have that -5 is less than the pivot, 3 is greater than the pivot, 2 is equal to it, so we'll allow that, 1 is less than the pivot, negative 3's, both of those are going to be less than the pivot. And 7 and 2, we'll just grab the 2 from that. So these are all of the elements that are less than or equal to the pivot. The right side will be the elements that are strictly greater than it. So we have negative 5, nope. 3, yes, that is bigger than the pivot. 2, no. 1, no. Negative 3's are not. We have 7, and it's actually just going to be 3 and 7. And then we do this recursively. So this left side here, this is going to be split again into 3 different pieces, where the pivot is actually still going to be 2. So in the middle, we will just have the list of 2. And the left side will actually be all of this stuff here, because we had a pivot of 2 last time. And so here we already broke this into the things that are less than or equal to 2. So this is actually going to be all of those things here. And we don't include the 2 again, because that's already the part of the pivot. And the right side is actually going to be nothing. That was what we call a bad pivot. And that's the problem with quicksort sometimes, is if you pick a bad pivot, then it turns out to be less efficient. You can see here, we didn't really do any useful work here. Now the 2 is at a base case because it is a sorted array of just one element. The 3 and the 7, we will make the 7 the pivot, and so the middle is going to be just the list of 7. On the left side, we would have just the list of 3, and on the right side, we have just an empty list. Okay, and all of the empty lists, those are actually base cases as well, because an array of nothing is also sorted. This array here will have a pivot of negative 3, so the middle is going to be just the list of negative 3. The left side is going to be just negative 5, and also the other negative 3, and the right side is going to be 2 and 1. Okay, we have a little bit more work to do here. This is going to split into just negative 5 with the pivot of negative 3. The right side is going to be nothing, and 2 and 1, that is going to split into nothing on the left with the pivot of 1 in the middle, and the right side will just be the list of 2. Okay, now notice here, all of these things are sorted arrays. They're all 1 element or 0 elements, and these are all sorted arrays as well. And so basically you just need to merge or combine these things together. And that's pretty easy because we actually split it into, well, this is all the elements less than or equal to the pivot P, and these ones are all the elements that are greater than P. So because of that, the merging is literally just the concatenation of these arrays together. Negative 5, negative 3, and nothing. That is going to make just negative 5 and negative 3. Okay, let's merge these together. It's going to just be nothing with 1 and 2. Now notice this array is sorted, this is sorted, and this is sorted as well. We want the list of negative 5 and negative 3, and 1, and then 2. Okay, if we combine these together, we are going to get the sorted array of negative 5, negative 3, 1, 2, and 2. This is already sorted. We combine these together to just get the array of 3 and 7. Okay, and if you were to combine all of these things together here, you would get the sorted array. So we get the full sorted array here. And that would be the end of your algorithm. Okay, now let's go back a step here to think about time complexity. And actually, let's just expand this base case here so we have a full proper level here. So if we have one full level of stuff here, so all of this horizontal line here, well, you have n things here. So if you have n elements in your array, here's all of your n stuff in one level. And basically, you would take these 3 pieces and merge it into one sorted array. You would take just this, which is by itself, into a sorted array. And you would take these 3 pieces and sort that as well. Basically, what you're doing is just taking all of this stuff, combining it with this, and then you have this combining it with itself, and these things are combining as well. So this is basically an O of n operation to merge one level together. And so if you pick a good pivot, it turns out that the height of this recursive tree at the full depth of recursion will be roughly log base 2 of n. So that's if you keep picking a good pivot, that's going to be the case. And so if you have a height of log of n, and then to complete one level, it is going to be an O of n operation, then you get a total time complexity here of big O of n times log n, which is very, very fast, but again, that assumes a good pivot. If you keep getting a bad pivot, so notice that we sometimes got a bad pivot. 2 is a really bad pivot here. It doesn't really help at all. So if you keep getting bad pivots, technically the worst case runtime of this is O of n times n, which is just O of n squared. But in the average case, you'll get a decent pivot. And so this is in the average case, you'll get an n log n time complexity. And the space complexity of this, the minimum space is going to be from the recursive call stack, although we'll see we'll actually code a O of n space just because it's a lot easier to do. Okay, so let's code up a quicksort. Okay, now let's do a quicksort, and it's a lot easier to code than merge sort. It has a time complexity of big O of n log n. So that's the average case. Technically, the worst case is O of n squared, and the space complexity, the minimum it would use is log n, but what we're going to write is O of n. Now, this is also a recursive algorithm, and so we need a base case case here, if the length of the array is less than or equal to 1, well then we would want to return our array. So if you end up with an array of size nothing or an array of 1 element, then those are both sorted, and so you would just return that array. Now otherwise, if it's not a base case, then you would need to split it into its 3 pieces. We get our pivot is equal to the array at the last index, which you can just write as array at -1. And then you'd get your left side is equal to, you can actually use some cool list comprehension for this. You would do the list of x for x in the array of everything up until, but not including the last index, if the x is less than or equal to p. Okay, so this is everything in the array, not including the end, that is less than or equal to p. And then very similarly, you can do this with r, except r is going to be all of the stuff in there if x is strictly greater than the pivot. So now we have it in our 3 different pieces. We have our pivot in the middle, we have everything less than or equal to it, and we have everything greater than it. Now the clever part of quicksort is here, which is L is equal to the quicksort of L, and R is equal to the quicksort on R. So you get your 2 big arrays here, L and R, and you want to recursively sort them as well. So we sort them by doing it on the recursion, and then once you are back here from those recursions, you want to return the array, which is the sorted version, which is just the concatenation of all 3. It is L, because L has now been sorted. You combine that with your pivot, which is the middle, and you combine that with your R on the right. And then you would just run a quicksort on E. We will again see that same sorted array. I think quicksort is really, really cool. Okay, now let's do a really cool sorting algorithm called counting sort, and this one definitely has the most implications for solving LeetCode problems. There's some clever problems you can solve with this to do some great optimization. So for counting sort, the first thing you get is the max value, so I'll just call that maxx. You would go through the array, find the maximum value, and see that it is a 7. Now firstly, you can do a counting sort with negative values in the array, except it is a little annoying to do that, and so for us, we're just going to use an array of positive values. So we're just going to take all of the negative signs out of this, and we'll do the counting sort on this array. Although you could do it with negative values, it's just harder. Okay, so we get the max value of 7, and the reason for that is because we're going to create a new array, which we will just call counts, and it's going to have max plus 1 positions, as in we're going to have the position 0, 1, 2, 3, 4, 5, 6, and 7. So that is 8 many positions, or max plus 1 many positions. Okay, so firstly, you would just initialize counts to be a bunch of zeros, and basically what this is representing is how many zeros we have in the array, how many ones we have in the array, how many twos we have, and that's why we need to go up to the max. So the first step of counting sort is to count the values, and so basically you would just send an index, we'll call it I, through the array, and then every time we see a value, we're going to use this value as the index and say, okay, for the 5s, we've seen 1 more of those. We'll increment this by 1. We would then move I over and see that we see a 3. Okay, we have 1 more of those. We see a 2. Okay, we have 1 more of those. We see a 1. We have now seen 1 of those. We see a 3. Okay, cool. We actually have 2 of those so far. We see another 3. Okay, we've seen 3 3s. And we would just send this through the array, and it's going to end up as the total number of each of the elements that we have. So after we send I through the array, this is going to be our counts. And as a quick check here, just make sure if you sum all of these values together, you get the size of your array. So we'd have 4, 7, 8, 9 many elements here. We have 9 many elements in the original array. Okay, so that's step 1 of counting sort, is to build this up. And then basically what you would do after that is we'll get an index I at the beginning, and we basically just try and rewrite this array. And so that's why the only space we use up here is actually this counts array here. We are going to rewrite this original array, so the only space we use up is over here. Okay, so we have an index I here, and then basically you would have an index C over here. And then you would kind of just move C over, and you would tick down this thing in a row. So we see that we have 1, 1. Okay, we are going to decrement that, and now we have 0. We are going to replace this element with a 1. Now we don't need to do any swapping. We don't need to put this 5 anywhere else because we've already kept track of it in the counts over here. Okay, so then we would move over I, and we would move over C. We basically have 3 iterations to run over here. So we would set this to be a 2. 2. We have 1, 2 there. We decrement this down to 2. Okay, we still have a 2, so we move over I. This position is going to be a 2. We decrement this down to 1. Okay, this position is also going to be a 2. This goes down to 0, and that is when we move over C. Okay, so this tells us the next 3 values are going to be 3s. So I'll stop using I, but basically all 3 of these next positions are going to be 3s. We would decrement this down over time to 0. We'd move this over here. It's going to set this one to be a 5. And when we get over here, it's going to set this one to be a 7. And in a very clever way here, we've rewritten the original array to be the sorted version. Okay, so let's think about the time complexity of this. Let's let k be the max value. So we'll just call this k for this discussion. Well, then we first have to create this array of k many values. And so that is definitely an O of k thing to do, even just to create the empty space for that. Also, to even find out what the maximum value is, you would have to traverse this array. And so if there's n many things here, well, then you'd also have to do an n operation to get the maximum. And then to fill up the counts array to actually figure out its values, you would do that through, again, going through the n things. So that's, again, an n thing to do. And then the final step of this would be to get your index c here, get your other index I, and then we can see I is basically just moving through the array. So that's another n thing to do. And then you're also incrementing c, and it's getting stopped whenever there's bigger values. So we'd have 3, that goes down to a 2, it goes down to a 1. It basically gets stopped here. It gets stopped basically n times because there's n things. So in total, it turns out that actually the total time complexity of this algorithm is big O of k plus n, where k is the max of the array. And the space complexity, you actually are overwriting the initial array, which means the only space we're using is in this counts array, which is going to just be O of k. So this is actually a really profound thing in computer science, that there is actually a linear sorting algorithm if k is small. So if k is really big, like if the maximum value is, 10 million, well, then this algorithm sucks. Like you basically have to do 10 million things multiple times. It's really, really slow. However, if k is small, which sometimes this is true, like if you have an array that's made up of only 1s, 2s, and 3s, for example, if you know that, well, then if k is just 3, well, then this actually approaches an O of n algorithm. And so what's so cool about this is we actually do have a sorting algorithm that is roughly O of n if k is very, very small, which is super cool. And if we did allow negative values again, so let's say that these were negative values here, well, it's a little harder to write this array because then you'd kind of have to have negative indices. And so there's kind of a transformation to do that. It's a little annoying. But then you would have k as the range of data. So basically the difference between your maximum of 3 and your smallest value of -7, you could keep track in theory of how many -7s you have, how many -6s you have, -5s, and so on, up until how many 3s you have. If the range of your data was small, well, then that's still an O of n algorithm, even for negative data. So let's code up a counting sort. It's really, really cool. So this has a time complexity of big O of n plus k, where k is the range of the data. Now I'll just add a note here. This can be written with values with negative numbers, except we'll just stick to positive arrays because it's easier. And so because that's the case, k is just going to be the max of the array. And so the space complexity here is going to be big O of k. Okay, so look at that same array we used there, call it f, and we will define a function called counting sort, which takes an array. As usual, we get n is equal to the length of that array. And the first thing we need to do is get the maximum value. So we'll get max with 2 x's is equal to the max of the array. And now we know the bounds of our count array. So we can set counts equal to, by default, we'll just have it as a list of zeros, and we'll have it as max plus 1 zeros. So that means the valid indices here will be 0 up until the maximum value. Okay, then we'll go through for each number x in the array. We will just collect the counts, and that is counts at x is going to go up by 1. The index is referring to the number that we have, and so we're saying that number, say 4, well, we have 1 more 4s, for example. Okay, then the more difficult part of this is you would set an index I equal to 0. That's the one that's going to be going through the array. Then you would set an index c in a for loop in the range of max plus 1. So this says go over all of the valid positions of 0 until max. Notice it lines up with that. Okay, then what you would actually do here is that while you have counts at c is greater than 0, you would want to basically decrement 1 from the counts, and you'd want to move over your index I after saying that that number is that position. You would want to set array at I equal to c, I plus equals 1, and the counts at c is going to go down by 1. It's saying we have this value. Okay, we have 1 more of these values values. We will set array at I equal to that value. We would move over I to adjust that position in the array, and we would decrement 1 from our count. Okay, and that actually is a counting sort. So we'll call counting sort on F. That is going to do it in place. Notice we rewrite the original array here. We rewrite or overwrite array. And so if you are to output F, you would again see that sorted order there. But here's what we usually do in practice. Now we generally use the word sorted or dot sort, and we'll see that in a second. And the time complexity is going to be O of n log n from using an algorithm known as timsort, which we didn't even talk about. It's rather complex, but it was actually written for the Python language, which is pretty cool. If you had some array, say G, if you wanted to do it in place, which means you wanted to sort it using constant space, you basically just rearrange these positions in the memory. Well, then you would call g.sort. That sorts it in place. And so if you output G, you will see that it has now been sorted. If you wanted to not do it in place, and there's certain times when you would want this and certain times when you have to, then you would want to get a new sorted array, which is going to take up O of n space. So if you had some array, say H, well, then you could get a sorted version of H. Notice that we're using the return value of this. So sorted H is equal to the sorted value of H. This thing is returning to us a new sorted array. And so we can actually output both of these. So you have H, which is completely the same, untouched as it was, and you have the sorted version of that array as well. Okay, now something else I wanted to throw in here. There's actually some really clever things you can do with sorting. So you can actually do, for example, sort an array of tuples. So let's say we had an array I where each of the positions are actually tuples. So this is -5, 3, this is 2, 1, -3, 3, and so on. Now you'll get this definitely if you see a problem called intervals, and it comes up in more than just that, but if you see any interval problems, it will likely involve sorting an array of tuples. And so what you could do is we'll call it sorted I is equal to the sorted version of I, but then you pass this thing called key, and you set that to be a lambda function, which I'll explain in a moment, which takes a tuple t and it returns t, we'll say t at 0 for now. So if we output sorted at I, then you're going to see this sorted by the tuple's first position. So this lambda function, it's just a function that says, okay, give me one of the things that you're trying to sort here. Okay, it's a tuple, we'll call it t, and this is what you'd want to do the comparison based off of. The first positions here are increasing. If you wanted to do this by the tuple's second position, you could do t at 1, and notice now that based off of the second position, these things are increasing. Okay, and if you wanted to do this by sorting in the reverse direction, so this would be -t at 1 means sort backwards based off of the second position, we would see 3, 2, 2, 1, -3. So now it's sorting in reverse order based off of the second position of the tuple. Okay guys, as usual, you can check the code in the description of the video. I hope this was helpful. Drop a like if it was, and have a great day. Bye-bye.